morning, one and all. This is Dr. Diana here. Welcome to the session on computer organization. And in the previous session, we have been looking into the instruction cycle. The instruction cycle basically has four phases. The first phase is the fetch. The second phase is the decode. The third phase is the operand fetch. The fourth phase is the execution. So before execution of a particular instruction, you make arrangements for that instruction to be executed. So that's what we deal with in the phases of instruction cycle. So in the instruction cycle, we see that the fetch and the decode phase are common for all the instructions. So we have seen and all these instructions are coordinated using timing signals T0 to T7, and we have these timing signals which are maintained by the sequence counter. So the sequence counter is responsible for creating timing signals T0 to T15, or every time an instruction is executed before timing cycle T15, the sequence counter is set to 0, or it is cleared to indicate that it should start counting from T0 once again. So based on this aspect, we have seen time cycle T0 to T15 can be used for instruction execution, and T0 to T2 are going to remain the same for all types of instructions. So at T0 we bring, the first thing is to read the instruction or the instruction fetch. For doing the instruction fetch, we identify the memory location of the first instruction to be executed, which is available in PC. The PC content is moved into address register because the PC cannot directly access the memory. Any access to memory is done only through the address register. So we have the address register that can be used here. So at time cycle T0, the content of PC is moved into address register. And at time cycle T1, we look into memory and read the instruction. Once the instruction is read from memory, it's available on the common bus structure, and from the bus it is directly given into the instruction register. The memory location M of the address given in AR is transferred into the instruction register, and then the value of program counter is, or PC, is incremented by 1 to indicate where we can find the next instruction. And at time cycle, these two indicate the instruction fetch. And at time cycle T2, we do the decoding of the instruction using the circuit that we have seen. The circuit has got two different decoders. The first decoder is from it's a 3x8 decoder which takes its input from the instruction register bits 14 to 12, and the second decoder uses the clock input and the sequence counter as input, and it generates 16 timing signals T0 to T15. So these two decoder signals are going to form the base of the control unit, and they are going to generate control signals D0 to D7 and timing signals T0 to T15. Once we have used at T2, we are generating the control signals D0 to D7 using the 14 to 12 bits of the instruction register. So there are 3 bits which are here, and a 3x8 decoder is used to generate the bits D0 to D7. And the MSB, or the most significant bit of the instruction register, is transferred into the flip-flop I, and we have seen that the bits 0 to 11, which are part of the instruction, indicate an address. Those are transferred into the address register. And at time cycle T3, we decide what type of instruction we need to execute. For doing that, we have seen the bits, the control signals generated from the bits 14 to 12 indicate that for a memory reference instruction, the value of D7 is going to be 0. If the value of D7 is 1, then it can either be a register reference instruction or an IO instruction. So based on that, we have identified, based on the value of D7, value is 1, it indicates either a register reference or an IO operation. Once we have decided on whether it's memory or register, we can now see whether it is a direct memory access or an indirect memory access based on the bit 15 or the I flip-flop. So I look into I. If the value of I is 0, it indicates a direct memory access, and if its value is 1, it indicates an indirect memory access. In the case of register or IO operations, the value of I being 0 indicates that it's a register reference instruction, and the value of I being 1 indicates an IO operation. So this is our initial understanding of the system. Once this is ready, we have shown them using control signals and timing signals that I-D7T3 is a register reference instruction, and I-D7T3 is an IO instruction, I-D7-T3 is a direct memory access instruction, I-D7-T3 is an indirect memory instruction. Now in this session, we are going to look into what are the different instructions available under the register reference category. So we are going to list our instructions one by one and see how that instruction is executed at time cycle T4 or at time cycle T3. Some of them may require time cycle T4, but most of them are executed at time cycle T3 only. Because we have only done some checking at time cycle T3, the execution will start at time cycle T3 itself. Okay, so at time cycle T3, under this condition, we are going to do the register reference instruction. So all register reference instructions are going to have the value I as 1, the value of I as 0, so I have to mention it as I dash. The value of D7 is going to be 1, so I have to mention it as D7, and it is going to happen at time cycle T3. Done. Now this I am going to represent using a word R. I'm just using a symbol R to indicate, instead of writing this entire thing, I'm going to use the letter R to indicate. So every time I write the letter R, please understand that it is I-D7T3. Okay now? And in a register reference instruction, the format of the instruction is going to be like this. My first bit is 0. I dash indicates the first bit, it's 0. And D7 is indicated by 3 bits, 14 to 12 are values set to 1, followed by 11 bits. So I have bits 0 to 11. These bits indicates the opcode or the operation to be performed. Okay. In the basic computer that we are trying to design, we are having 11 different register reference instructions, which are indicated by placing a 1 in each of these 11 bits. Are we clear here? So my first instruction could be all zeros with the last 1. So how many do I have here? I have 8. I can have 11 bits with 1. The second instruction could be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. So only 1 bit out of the 11 bits is going to be 1. The rest of the bits are going to be 0, and the position of 1 in the 11 bits decides which operation I am going to perform in the register reference category. So this is going to be, I will use value B to represent the bit which is 1. So if I say B0, then it means that at location 0 or the instruction register least significant bit If I say B1, then it means that at instruction register, the bit 1 is 1. So this way I can understand I have instructions specified by B0 to B11, which are indicated by placing 1 in that respective position of the instruction register. So we are going to use B0 to B11 as the symbolic representation. Instead of using instruction register of the corresponding bit, I am going to use the notation as B0 to B11. I am going to now explain what are the 11 different instructions, register reference instructions available in the common computer or the basic computer that we are trying to design. The first few of them are going to be, most of these are as I say, it's a register reference instruction. Let me tell you what are the registers available in the basic computer. In the architecture that we have seen earlier, we have used an accumulator and a temporary or a data register. Instead of using a data register symbol, in the book they have used it as an extra register. It can either be the data register or it can be the temporary register. There are two different registers available for storing data other than the accumulator, which are temporary register and the data register. For now, both of them are considered extra registers, and the instruction is set denotes it as register E. So there is register E can either be a temporary register or the data register of the basic architecture we have seen earlier. So the first few, all these instructions are going to be on either the accumulator or on register E. The first instruction here is the CLA. Now, in a machine like this, we are going to use symbols to represent instructions. These symbols are also called as mnemonics. These are called as mnemonics. All the instructions are going to be represented using symbols. And I can either specify an operand to go along with the mnemonic, or I can indicate the operand also part of the mnemonic itself. Here in this example, if you see, I have mentioned it as clear CLA. CLA means to clear the accumulator. Now the operation that I do is the clear operation, and the operand or the data on which I perform this operation is the accumulator. So both the data and the operation are specified in the mnemonic itself. In all the register reference instructions, the data is also specified part of the mnemonic. So I don't have any other requirement to specify the operand. The operand is specified part of the instruction itself. So part of that 11 bits is sufficient to explain both the instruction and the data to be used for the instruction. So if I say the first instruction is clear accumulator, I should represent it as I dash D7 T3, and the value of the bit which has to be 1 is B0. It is B11. So it is B11 for clear accumulator. B11. At this point of time, I should clear the accumulator. So I can write it as, I can load 0 into the accumulator. So this is my operation. This is how I write my operation for the instruction CLA. Or in other words, I have, instead of writing it so complicatedly like this, I said we will use the letter R to indicate this entire thing. So I can write it as RB11. At RB11, I am going to clear of the accumulator. Now, I have said that this R represents I-D7 T3. Because all register reference instructions can be completed in the same time cycle T3, once the time cycle T3 is complete, I need to clear the sequence counter so that I can start executing my next instruction. To do that, what I should do? I should clear the sequence counter. So I should clear the sequence counter to 0. Because this is common for all instructions under the register reference category, I can indicate that R means not only I-D7T3, but it also means the SC has to be cleared. Are we clear till here? So after performing the T0, T1, T2 time cycles, at time cycle T3, if it's a register reference instruction and if B11 is 1, then I have to perform clearing of the accumulator followed by clearing of the sequence counter. Once I clear the sequence counter, it means that the instruction execution is complete. I can get back to time cycle T0. Are we clear? So this is how it works. Now I have given this for one particular instruction. We are going to do this for all the 11 instructions of the register reference category. In your examination, this question is going to be very, very important. So they'll ask you either to explain how the hardware is designed or the micro operations available for register reference instruction or memory instruction or IO instruction. So these three are very important questions part of your unit 1. Which is why I am taking so much time in explaining these concepts. Okay. So before I explain each instruction, for all instructions, R indicate I-D7, T3 and the SCB cleared to 0. And BI is, what is BI? It can be either B0 to B11. BI is the bit of IR of 0 to 11 that indicate a specific operation. So it can be either B0 to B11. So this is our understanding. So this is going to be common for all the 11 instructions. So we'll write instruction by instruction and see how these work. Okay. Now the first instruction that we will see is, we have written already, first instruction is the clear accumulator. What does it do? I'll write the description here. Clearing of the accumulator. And what mnemonic timing signal should I use? R, B, 11 low, accumulator should be cleared. This is the mnemonic representation of the required instruction. Is it clear there? Yeah, okay. The second instruction is the same clear but for register E. So I have to write it as CLE. E represents the data for which the execution has to be done. So this is clear register E. This is done with same R. R indicates I-D7T3 and the clearing of the sequence counter, followed by bit 10. At that point of time, I am clearing the register E, or I am loading the value 0 into the register E. The third instruction is CMA. CMA means to complement the accumulator. Complement means to invert the ones into zeros and zeros into ones. That is called as a complement operation. So CMA means complement of the accumulator. This happens at RB9, and here I load the accumulator with the complement of the accumulator. It is mentioned as AC bar. Yeah, so this indicates that the complement is loaded into the accumulator. The fourth instruction is CME. CME means complement of, note down, it is not COMPLI, it is COMPLE, which means the complementary of things. Okay? Complement of register E. The timing information is RB. This is called as the timing and the control information. So this indicates at what time, with what control signals this has to be performed. So this is called as the control information for performing that particular instruction. So I can write RB8. I have to replace the content of the register E with its complement value. Clear? So this is called as the complement of the E register. The fifth instruction is CIRA. CIRA. Or I can also use this as CIR. Okay, this means circulate, write the accumulator register. Now imagine I have some content to be circulated right. What is a circulate operation? In a circulate operation, what should I do? Imagine this is my value that I am trying to circulate. So I have taken a 4-bit example here. I've got 1011 as my bits. If I try to circulate them towards the right, I need to move all the bits by one position right. So when I move that, I'm moving the bit MSB to the next position 101. This one becomes my LSB, and the LSB of my input has to be moved back into the first position, or this MSB. So it should become 1101. This is called as a circulate operation. Now to perform this operation, I need some temporary register where I can store this value to. Right? Now, when I just move them right by one position, if I write this bit here, this bit here, this bit here, one of the bits will be overwritten. To avoid overwriting of that LSB, I have to save this LSB to some place and then perform the circulate operation. Bring this LSB from the temporary place into the MSB. That's how the operation is done. So, this can be indicated as RB7. The first thing that I do is I have to safeguard my LSB. The LSB is 0th position of the accumulator. The 0th position of the accumulator is pushed inside the extra register. Then I perform a shift right operation. Shift right operation is nothing but moving everything one bit right side. So I can load the accumulator with the shift right SHR of accumulator. I've shifted everything one bit to the right. Now I have to bring this LSB which I saved in the extra register into the MSB of the accumulator. which is represented as accumulator of 15. So 15 is the MSB. To that position, I should bring the content of the register E. Clear? Are we clear till here? So this is how a circular write shift is performed on the accumulator. The sixth instruction we have is CIL or CILA. It is circulate left of the accumulator. So this can be done using the control information RB6. With the control information RB6, we have the accumulator content. In this case, if I try to shift everything towards the left, which bit should I say? Imagine this is my 4 bits that I want to preserve. When I shift everything to the left, the MSB is the one that will be overwritten. So I have to save only the MSB. So I am going to save the MSB of the accumulator, which is bit 15 of the accumulator, into the register E. Then I am going to perform a shift left operation of the accumulator and store the result back into accumulator, followed by I have to now bring this bit into the LSB. So I am bringing the bit from register E into the 0th bit of the accumulator or the LSB. Are we clear till here? So this is called as the circular write of accumulator. The 7th instruction we have is increment. Increment always is done on the accumulator only. So it's called as increment accumulator. So the control information is RB5. Accumulator is loaded with accumulator plus 1. Instead of loading this accumulator plus 1, I can also raise the increment signal of the accumulator. So it's more like a hardware signal that has to be generated for this particular instruction. The 8th instruction in the register reference category is the skip instruction. Now we are going to look at 4 different types of skip instruction. Let me write here. The first skip instruction is SPA. SPA. SPA means skip if positive. I am going to look into the value of the accumulator. If the value of the accumulator, whatever content is there in the accumulator, if it is a positive value, then I have to skip the next instruction. Okay, this is what skip if positive does. How do I perform this operation? Now the first thing I need to do is find out whether the accumulator content is positive or not, and if it is positive, then what should I do? I should skip the instruction. How do I skip the instruction? How does the computer know which is the next instruction? From the value of PC. Imagine my PC value is 5. Means the next instruction that I want to execute is at memory location 5. If I say I have to skip this instruction, then it should, instead of executing the instruction at location 5, it should go into location 6 and then start executing that instruction. That's how it should work, right? So I'll check if it is positive, and if it is positive, I'm going to increment the value of PC by 1 so that you can skip one instruction and move over to the next. How do I find out if a number is positive? When do I say the number is positive? The number will be positive if to understand that you should see how many bits are there in your data. All data which is read from our memory is of 16 bits wide, and in any representation the MSB is used for indicating the sign of the number. So this MSB is called as the sign bit. So if my 15th bit of the accumulator is, when is it 0 and when is it 1? The value is 1 if the number is negative. The value is 0 if the number is positive. So I am going to do with control information RB4, if my accumulator's 15th bit is 0, then I am going to increment the value of PC and store it back into PC. This is called as skip if positive. Now tell me, how should I do the next instruction is SNA skip if negative. It happens at RB3 if, what should I check here? The accumulator's 15th bit, if it is equal to 1. Very good. Then the value of PC will be incremented by 1. So PC is equal to PC plus 1. And this is called as skip if negative. This next instruction is skip if 0. So skip if 0 means this is also done only on the accumulator. The control information is RB2 if the accumulator is 0, the entire content of the accumulator is 0, then I should skip, then I should increment the value of PC by 1. Are we clear till here? So this is called as the so this is called as the skip if 0 instruction. The last 11th instruction is HLT, which is halt. Halt is to stop the computer's operation. For doing that, there is a flip-flop called yes, which is called as the start stop flip-flop. I just have to clear that start stop flip-flop. So at RB1, the start stop flip-flop will be cleared to 0. This is called as the halt instruction. So today we have seen all the register reference instructions. All register reference instructions are completed at time cycle T0. And we have seen at T0, we fetch instruction at T0 and T1, we decode instruction at T2, and at T3, if D7 is 1 and if D and the value of I is 0, then we perform a register reference instruction. We have got 11 different register reference instructions. And for all of the 11 instructions, the value I dash D7 T3 is the control information, and after the time cycle T3, the sequence counter is cleared to indicate the completion of execution of that particular instruction. We also noted that all the register reference instructions are completed in time cycle T3. So at time cycle T3 itself, we can clear off the sequence counter. And B is the bit which is used to indicate the operation specified in the instruction register. So instruction register has got 11 bits. Only one of the bit is going to be 1 at any point of time. Depending on which bit is 1, particular instructions are performed. If bit 11 is 1, then the instruction is called as clear accumulator. Accumulator's value is cleared. If its value is B0, clear of E register. If its value is 9, then the complement of accumulator, complement of E register, circulate operation for right, circulate operation for left, and then we have the increment operation. Then we saw 3 different skip operations. One is all of them take accumulator as the input or the operand. So they check the value of accumulator. If it's positive, one of the instructions is skipped. If it is negative, if one instruction is skipped. The next one is if the accumulator's content is 0, one instruction is skipped. The last register reference instruction is the halt operation. So the halt operation is done by resetting of the start-stop flip-flop, which is indicated by S. With this, I'm closing for today's session. In the next session, we will look into memory reference instruction. Stay home, stay safe. Looking forward to seeing you all soon. Thank you.